Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at industrial rocks and minerals and their importance in society. So in previous videos we've been focusing on metallic minerals. We've been looking at things like gold and silver, copper, lead and zinc, but industrial rocks and minerals are not exploited for metals. They are exploited to produce materials which are used for industrial purposes. So we're thinking about the extraction of limestone to make cement, or maybe we're thinking about clays which are extracted to make bricks. So industrial rocks and minerals are non-metallic resources, and they are not mined to extract a metal or some kind of energy source. So we're not accessing them to get hold of oil or natural gas or uranium, for instance. So some of the common uses for non-metallic resources include construction material. So that's going to include things like sands and gravels and limestones, clays and gypsum in the form of drywall. But they're also going to be used in agriculture. That's going to include phosphates, nitrates, and potassium compounds, which are used to make the fertilizer that feeds the crops. There's going to be a range of industrial uses. That's going to include things like rock salt, sulfur, and asbestos. Now, asbestos isn't really used anymore, but once upon a time it was used for a significant number of industrial purposes. We are also going to use industrial rocks and minerals as gemstones and abrasives. Now, to be clear, we're not talking about the kind of gemstone that's going to go in a piece of jewelry. What we're looking at are stones which are going to be used as abrasives, so on cutting tools and polishing tools. And so having very, very hard minerals is very important in order to successfully polish hard materials. So if you're trying to polish a very hard material, you are going to want an abrasive that contains diamonds because it's the naturally hardest occurring mineral. Same with corundum as well. So corundum is aluminium oxide, and it has a hardness of 9 on the Mohs scale. So this is amongst the second hardest minerals out there. So once again, if you crush it finely enough, it's going to make a very good abrasive for polishing and smoothing materials. And then we have industrial rocks and minerals which are used for household and business products. That's going to be things like glass sand. It's going to be things like fluorite for toothpaste. We're going to have diatomite, which is used in things like gardening purposes. We've got graphite, which is used for things like pencils. And we have borax, which is used in some types of laundry detergent. So none of these types of industrial rocks and minerals are, as exciting as the metallic minerals. So a lot of the time, industrial rocks and minerals are kind of ignored because they're not seen as being as much fun, to be honest. But they are extremely important for society to function properly. Okay, so let's begin by looking at cement, concrete, and sheetrock. So although limestone can be used as a building material in its own right, a significant proportion of extracted limestone is actually used to make cement. So as limestone is what's considered to be a low value bulk material, it's typically mined in open pits because underground mining just doesn't make sense. It would be too expensive. So if you look over here on the left, you can see here's a limestone quarry, and you can quite clearly see the pit right here where the limestone is being extracted. So the limestone will be mined, and you will try and select the best quality limestone you can, because you're going to want to avoid high levels of impurity. So you don't want too many clay minerals in your limestone because that's going to produce a slightly lower quality cement. You're also going to be trying to avoid things like layers of limestone which are very, very rich in fossils. Because if you just use a block of that limestone for building a building, well, those fossils are going to be natural weak points. And over time, as that limestone starts to get weathered, it's going to fail, first of all, where those fossils are located. So if you're trying to dig up limestone for cement, you want to try and avoid clay minerals. If you're going to use your limestone as a building material to make limestone blocks, you want to try and avoid limestones that contain excessive amounts of fossils. And so there's a lot of quality control that's required to make sure you are collecting the correct material in the first place. So the limestone for cement is crushed, and once it's crushed, it's sent to a cement plant, which uses a two-stage process. So the first stage that your limestone is going to go through is it's going to be heated in a kiln to temperatures between 900 and 1050 Celsius in a low oxygen setting. And this is going to produce the following chemical reaction. It's going to take your calcium carbonate from your limestone, and it's going to split it into quicklime, calcium oxide, and carbon dioxide. And so the carbon dioxide is just going to be vented to the atmosphere, and the quicklime is going to be mixed with clay minerals or pieces of shale rock. And depending on the purity of your limestone, you may also add in bits of iron ore, you may add sand, bauxite, fly ash, and slag. So depending on the quality of your quicklime, you may need to add in other components in order to improve its quality. So once you have your quicklime and you've mixed it with all these other materials, you are then going to heat it to 1450 Celsius. And this is known as the fusion temperature. And this is the temperature at which quicklime will react with aluminium silicates. And these are the aluminium silicates that we deliberately put in with the quicklime in the form of clay minerals or pieces of the rock shale. And this is going to produce a range of anhydrous, so water-free, calcium silicate minerals. And it's these calcium silicate minerals that actually make up the cement. So the second stage of the fusion temperature will produce balls of calcium silicate minerals, which are referred to as clinker. And this clinker is then crushed to form the grey powder, which we call cement. And typically, the powder, which consists of these calcium silicate minerals, will often be mixed with about 5% gypsum. And this is because gypsum helps to control the setting time. It helps to stop the cement from setting too quickly. And so you can see that you have several different industrial minerals being used in the production of cement. You obviously have the original limestone, then you have clay minerals, or you have pieces of shale which are required. And depending on the quality of your quicklime that's produced, you may need to add more limestone, you may need to put iron ore in, or sand, or bauxite, or fly ash, or slag to improve the quality of your quicklime. And so at this stage, you can see we've added additional industrial minerals to the limestone that we initially put in. And then at this point, once we have gone through the fusion temperature and produced our calcium silicate minerals, we're then going to also add in some gypsum, another industrial mineral, in order to help control the rate at which our cement will turn into concrete. So when your cement powder is mixed with water and aggregates, so aggregates consist of sand, gravel, crushed stone, it will produce something which we refer to as concrete. And so if we look at this diagram here, you can see how concrete is, well, what concrete is actually made of based on percentages. So it's going to be about 40% crushed stone and gravel, that's your aggregate. You're going to put in about 25% fine aggregate in the form of sand, about 16% water, 11% cement, and 6% is going to be air. So the actual amount of cement involved in making concrete is actually surprisingly low. So the cement powder will act, or the cement powder, which when mixed with water, will produce a chemical reaction that will cause it to harden. And that means that it will essentially cement the aggregate in place. It will hold the pieces of aggregate together. And so even though it only makes up about 10 to 15% of the mix, the cement powder is very important because that's what's actually holding the pieces of rock in the cement together, and that's what gives it its strength. Now, in the case of drywall, which is also referred to as sheetrock or gypsum board, it's commonly used for home building in the United States. So gypsum is an evaporite mineral, so it's formed by the evaporation of water. And it's a low value bulk commodity, so it has to be mined in quarries because underground mining, once again, wouldn't make sense. You've got to mine it using an open pit method. And once you have mined it, you then need to crush it to produce a fine gypsum powder. Now, once you've produced your gypsum powder, you are then going to dehydrate it. And this is going to involve putting it into a kiln and heating it up to drive off the water which is contained within the mineral gypsum. So once you have dehydrated your gypsum, you are then going to end up with a powder of anhydrous gypsum. And then you're going to mix that powder with a small amount of water and some kind of fiber. And that fiber could be a paper fiber or it could be fiberglass. And then you're going to take that mixture and you're going to compress it to form a board. And that is drywall. It's just a mixture of powdered gypsum, a little bit of water, and some kind of fiber that's been put under extreme pressure to form it into a sheet. So in terms of cement making and drywall production, both of them are extremely polluting processes because they typically use coal in order to heat the kilns and drying ovens involved in making cement and drywall. So industrial minerals, although not as complex to process as metallic elements, they still require a lot of work. They still require a lot of energy, and the process of making them, taking cement and taking limestone and turning it into cement is a very energy intensive process that does produce a lot of pollution. Okay, so now let's move on to sand and gravel. So sand and gravel deposits are typically located within river systems, so stream systems. Now, the class size that you have is going to be controlled by the stream energy, with river systems that had a high energy forming quite coarse gravel deposits, and moderate energy river systems forming more sand-rich deposits. Now, the aggregate can be extracted from active streams by dredging, or you can extract it from dry streams using excavators. So, if we look at this plant here, what's happening? Well, we have a situation where we're going to have excavators just digging up the sediment from an old dry river, and it's going to feed it into this plant, and the plant's going to sort the sand and gravel into separate sizes and split it off and put it in separate bags for different uses. Let's see. So the aggregate can be extracted from active streams, or it can be extracted from dry streams using excavators. In terms of sand, the sand is used in brick, glass, and tile making, while gravel is used as ballast in construction projects, and it can also be used to concrete. And both of these, the sand and the gravel, are commonly used in cement production. So once again, we have another industrial mineral or rock that is used to produce another industrial material. Now, what you can also do to create gravels and sands is you can crush other rocks. And so crushed rock consists of harder rocks, so quartzite, gneiss, and granite. So these rocks are very, very rich in quartz, and they're very, very rich in feldspar, which are hard minerals. So feldspar has a hardness of 6 on the Mohs scale, quartz has a hardness of 7. So they're going to be very resistant to general wear and tear. The angular nature of the clasts which are produced by rock crushing makes it suitable for environments that require more friction. And so when you are building a road, you're obviously going to have your bitumen, which is going to hold your class together, but most of your road surface is going to be made up of crushed rock. And because that crushed rock consists of a mixture of quartz and feldspar, it's going to be very, very resistant to the constant movement of tires over your road surface. Another nice thing about crushed rock is that the source of the crushed rock can be controlled, and as such you can control things like the color. And so this means that crushed rock can be used for decorative purposes, for instance in gardens. So the next industrial mineral we're going to look at is silica sand. And silica sand is a very pure form of sand that is dominated by quartz. And it's produced in desert and beach environments. So typically when you have sand, you will see that it contains a mixture of both quartz and feldspar. However, the constant movement of the sand in desert environments and in beach environments will steadily, over very long periods of time, lead to even the feldspar breaking down. And remember, feldspar has a hardness of 6. It's a very robust mineral. So in order to make it break down, you need to work on it for a very long time. And so constantly moving it backwards and forwards in a desert, or constantly pushing it backwards and forwards due to waves, is enough to slowly but surely break down your feldspar crystals, leaving just the quartz behind. So after enough time, even the feldspar has been broken down and washed away, and so the sand you're left with is a very pure quartz sand. And this is primarily used in 2 things. It's used in glass making, and it's used in the production of computer chips. The next industrial mineral of interest is going to be clay minerals. So clay deposits can be formed in a couple of ways. The majority of clay deposits are formed by the weathering of a feldspar-rich rock, typically something like a granite. And so what happens is your clay minerals form in situ. So you have your granite, it weathers, and the clay minerals form and stay in the same location as the weathered granite. And the breakdown of the feldspars within the granite is going to be caused by simply the basic weathering process, or it could also be caused by hydrothermal fluids passing through the granite, causing the feldspars to break down and convert into clay mineral. Now, you also have another type of deposit, which is called a secondary clay deposit, and this is where you have clay minerals which have been transported into a confined area. And so this would be something like a lake, for instance, and then obviously the lake dries out, and then later on we can come along and dig up the clays from the bottom of the lake. Now, there are several important clay minerals, and 3 of the most important are kaolinite, smectite, and illite. So in the case of kaolinite, it's used in ceramics, it's used in pharmaceuticals, and it's used in cosmetics. In the case of smectite, it's an absorbent, so it's used in things like cat litter and for oil spills. It's also used for soil amendment. It's quite good at taking a very clay-rich soil and breaking it up a bit and making it drain better. And then you have illite. Illite is primarily used in brick making and cement production. So in terms of how we mine these clays, well, clay minerals are very, very soft, and clay deposits are very, very soft. And so we don't actually blast the rock. We don't even really use excavators. The vast majority of clay minerals are actually mined using high pressure water. So you're essentially blasting your rock face with this high pressure water, and it's essentially washing the clay minerals off the rock face, and then you simply collect that water, you take out the clay minerals, and then you use the water again to keep blasting away at the rock face. Our next type of industrial material is going to be salt. And so salt deposits, like gypsum deposits, form due to evaporation. So this is when we have a restricted body of water which evaporates away, and it evaporates faster than new water can come in. And the majority of large evaporite deposits are associated with bodies of marine water. So we're looking at seas and oceans. So mineable salt deposits are typically quite thick and they form nice continuous layers. And this is helpful for mining because typically when you mine something, you want it to be in one nice flat layer because it makes the mining easy. Now, salt can be mined using open pit methods, or it can be mined using underground methods. And in terms of salt production underground, relatively low cost mining methods make this possible. So even though salt is quite a low value product, you can get the cost of mining it underground low enough where it's still economic to do so. Now, in some cases, you don't actually need to directly mine the salt. You don't need to go down there and dig it up. Some companies actually inject water into the salt-bearing layer, and then they extract the recovered water, and then they remove the salt from it, and then obviously pump the water back down again to process. So in terms of salt itself, the main salt you're probably familiar with is halite, sodium chloride, otherwise known as table salt, and it's used in food products, it's used in the chemical industry, and it's used in industrial settings. Now, there is another common type of salt which is called sylvite, and that is potassium chloride, and sylvite is primarily used in fertilizer. It's where the potassium in fertilizer comes from. So salt deposits are very important. They are typically, quite soft deposits, and they form nice consistent layers, so they can be mined quite easily and quite cheaply. The final industrial mineral we're going to be looking at is phosphate. So phosphate is found in a class of rock which are referred to as phosphorite rocks, and these are simply a type of phosphate-rich sedimentary rock. And these sedimentary rocks are either typically limestones or shales, and they will contain high concentrations of phosphate at about 4 to sometimes up to 20% of rock. So how do we actually form these very phosphate-rich sedimentary rocks? So these deposits form on the continental shelf, and they form in areas where phosphorus-rich seawater upwells into shallow water. And so because this deep ocean water is coming up, it's bringing phosphate with it, and when that phosphate-rich water enters onto the shallower continental shelf, it essentially allows the phosphate to become incorporated into the sediments which are being deposited onto that continental shelf environment. In terms of why this deep water has these elevated concentrations of phosphorus in it, well, deep sea water builds up elevated levels of phosphorus from hydrothermal vents. So one of the elements that comes out of those black smokers and other seafloor vents, along with all the other stuff, one of them is also going to be phosphorus. And so that means these deep ocean waters will build up elevated concentrations of phosphorus within them. And then due to ocean circulation, sometimes that deep ocean water gets pushed up onto the continental shelf and the phosphorus becomes incorporated into the sediments being deposited on that continental shelf. And the primary use for phosphate is in fertilizer, because obviously plants need quite a lot of phosphorus in order to grow successfully. Okay, thank you for watching, everybody.